All right. So physicists, I need your attention right up here, please. This was the homework. I just didn't get it put up there that I assigned for homework for today. I'm just going to post or paste it right here. Boop. There you go. So, oops, but it's all frozen, so you can't see it. Ha-ha, there we go. Are there any of those problems that you or questions that you would like to go over? Anything from the homework from last night that you have issues with? Yeah.
Just problem 8.
Problem 8? Sure.
You have to key up on it.
I do. Yes, and I was going to ask if anybody had a chance or an opportunity to use the key or and did it work okay? Awesome. Okay. But yes, I'm super happy to go through problems as well. All right, friends. Shh. I'm glad. I hope that it is. I don't want you to feel like because I put that up there that I won't answer questions for you. I just think that it'll make things go a little bit faster. Yes. So Henry, you were asking about question 8.
Yeah.
What are the amplitude and frequency of the oscillations shown in the figure? Okay, so let's just take a look at this one. There's a lot of chitter chatter going on, and it's really hard to talk over you all. So can you please, stop? All right, let me switch this over here real quick. Okay, so amplitude. How do you find the amplitude of a wave or of an oscillation? Maximum displacement from equilibrium, right? Yep. So even though this one starts at 5, is that its equilibrium position?
No.
How do you know that it's not the equilibrium position?
Because it's the same on, if you look at the max and the minimum, it's the same, so equilibrium has to be 0.
Right. And that's something that's really important to know, is that when you're looking at those oscillations, the equilibrium is just where it's at the middle, not where it starts. So the amplitude is going to be 10, right? 10 centimeters?
Yeah.
And it's a positive or negative, so the amplitude is always just absolute value. Does that get you where you need to go?
Yeah, I did that one.
Okay, do you want me to talk about frequency too, or was it just the amplitude that was the
talk about
sticker?
The frequency just for one problem.
Sure. Okay, and so it just says, and then what is the frequency of the oscillation? So frequency, I think, did not explicitly say this yesterday, or maybe we did. I cannot remember. But period is measured in seconds, right?
Right.
And frequency is cycles per second. Here's one of those funny little equations that just is, and you just need to say, sure, that sounds good. If this is seconds, this is actually seconds per cycle. You with me there? Seconds per cycle, cycles per seconds. Hey, it must be what's the R word?
Reciprocal.
Reciprocal, that's what I was looking for. F is equal to 1 over T, or you can write that as T is equal to 1 over F. Okay? That's one of those things that you just, if you know one, you definitely know the other because it's just 1 over. Okay? So now we can find the period of this thing, right? We can find the period. We just have to find one cycle. Does it matter where we start?
No.
No. So we could start here. That would be okay. If we start here, it's going to go down. Is that one period?
No.
No, that's I don't even know, some of a period. So you could go to here. That looks about the same because that would be the same place in the cycle, okay? Which looks like about 2 seconds. Is that the frequency then?
You got it.
What is 2 seconds?
Period.
2 seconds is the period. So to find the frequency, you're going to do 1 over the period. So that's 1 over 2. Oh, that's a half, right? Half a hertz, 0.5 hertz. We good?
Yeah.
Sweet. All right. Any other homework stuff?
No.
Fantastic. Y'all were getting a little cranky yesterday about that last problem and then the bell rang and stuff. So let's just make sure that we're all good on that one. Last conceptual question. You remember? I don't know if you remember you were cranky though. Yeah, it's all recorded, so you can, watch it again if you want to experience that again. Let's not go with the crankiness, but let's have the conversation. This is going to lead into what we're going to do today, which is why I didn't want to just shut it down. I wanted to come back to it. If the amplitude of a system and is moving in simple harmonic motion is doubled, so that means a pendulum swinging and you double the angle, it means a mass on a spring bouncing back and forth, and you double the stretch, right? Any of those things. Oh, and remind me in just a second, I have to tell you one other really fun example of simple harmonic motion. Don't let me forget. Anyway, if the amplitude is doubled, which of the following quantities doesn't change? So let's back up for a second. Total energy, maximum speed, maximum acceleration, period. Think this through for me. Tell me an answer, but then we're going to go through all three of them to make sure we understand. Nick, go get it started. It's D, he says. Yeah. Why?
Because in our experiment, the period didn't change if you increase the angle of release, aka the amplitude.
Yeah.
Does that make sense?
Yeah.
We all did find that, right?
Yeah.
Right.
So regardless of what the amplitude was, the period stayed constant. So if it was at 5 and you moved it to 10, that's doubling the amplitude, and it does not change the period. Now, here's the thing that I really want you to get in your head. So this is kind of the funny thing. What is it that impacts the period? Or, yeah, what is it that impacts the period?
The mass.
Length. No, it's not the mass.
The mass, the length, the amplitude. What was it?
Length.
Just the length. So, and we'll talk about this a little bit more, but I think it's kind of interesting. How many of you have ridden on a swing before? You ever been on a swing before? Yeah? Have you ever noticed, like I remember this from when I was a little kid in elementary school, that you can have two swings that have the same period, like they go back and forth together, and so like you and your best friend might be swinging together and you might be on the same, like you might be swinging at the same, What do you know then about the lengths of those swings? They're the same. So if you asked your dad to ride on the swing next to you and you were sitting there and they were the same length, then even if your dad and you were sitting on those swings, and I'm assuming that your dad probably had more mass than you did when you were a kid. I'm just making an assumption. I don't ever want to whatever. No, that's what I'm saying. Making this clear. Regardless, does the period differ?
No.
No. What about if when you're swinging with your big sister and your big sister knows how to pump her legs, and so that means that her what is bigger?
Amplitude.
Amplitude. How does her amplitude compare, or how does her period compare with yours? If the swings are the same length. They're the same. There is, which is what we're talking about, right? So let's talk about that. Is there a change in energy if you're really, really high to start and you go versus if you start lower?
Yes.
Absolutely there is, right? How about the maximum speed? If you have two pendulums, one that is pulled back really far and another one that's pulled back here, and they're both going to take the same amount of time to get from here to here. Does that make sense? Because if their periods are the same, half of their period is going to be the same also. Is that okay? If it takes the same amount of time for a pendulum, let me draw that other, my pen went in my pocket. So orange pendulum versus blue pendulum. Okay? To get to the other side, which one has to move faster at the bottom? Blue, why?
Because it has more ground to cover.
Yeah, it has to go a lot further than the orange one does, right? Yeah, that's exactly right. And then talk about the maximum acceleration. What do you think about the maximum acceleration? You didn't choose that one. What's acceleration? Change in speed. Where's it going to experience the most acceleration? Yeah. Yeah. Where it has the biggest force. And hey, do you remember that we said that force was equal to negative kx, right? So at the biggest displacement, it's going to have the biggest force. And at the biggest force, it's going to have the biggest acceleration. You with me there? Yeah? Yeah? That's what we're putting together today. All right. Question?
If it's just free fall, like the only acceleration is gravity, how's the acceleration greater from one to the other?
Because, are you talking about in this case? Because the force, and we have not drawn this picture yet. So that's part of the reason I'm kind of like waving my hands a little bit. We will do this picture probably like Tuesday or Wednesday of next week. The force that's actually pulling the pendulum back to equilibrium is partially free fall and it's partially the tension in the string. Because if the string wasn't there, then this little child or this big person or whatever is just going to go straight down. You with me there? So it's the total force, the tension force plus gravity. You have to kind of do some vector stuff. We'll get there. Yeah. Does that make a little sense?
Sure.
For now in a hand wavy way. We will do it, like I said, next week. We'll like actually draw it out with the free body diagram. It'll be awesome. Okay, we ready to go? It's gonna be a good day today. I have a piece of paper that I'm gonna give you that's bright gold, which probably means what, do you know? It's important, keep it, don't lose it. This is like a good thinker paper. I'm not a big worksheet person. You guys have maybe noticed that this year, I don't know. This is one of those, like, think about it. It's got lots of good things to think about in it. What do you want to ask me? Oh.
I wasn't using it.
I know, I just figured it would be less distracting to me.
Yeah.
All right. So, as I mentioned to a few of you as I was walking by, I love this sheet, and I'm going to tell you why I love it. I love it because it requires a lot of thinking, and it also records a lot of the thinking all on one piece of paper and in one nice space. So I'm going to let you think in just a minute and start to fill some things in, but I want you to take a look at what's going on here first. So can you put your eyes up here just for a second? Probably should have handed or looked at this with you and then handed it out. But we've got a mass on a spring. We're going to assume that it was on some sort of flat surface so that it's not going to swing down, right? That would be more complex motion than we want to deal with. So it's going to slide back and forth this way. They just didn't put the surface there. We're going to assume that it is frictionless, so the amplitude is going to stay the same the whole time, okay? This is one of those ideal systems that physicists love and engineers don't. So if you have an engineer mind, put it away for a minute, okay? We're living in a nice fake world where we can have no friction and all that good stuff. So I'm going to displace this block to A. You with me there? And I'm going to let go. And it's going to go bouncy, 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 bouncy. And instead of just talking about it going bouncy, 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 I'm going to take some pictures of it. So there's one at the top, and then, oh my gosh, it goes through. What do you think this dotted line is representing?
Equilibrium.
You guys are awesome. Yeah. And then it's not going to stop there because it's moving. And if an object is moving, it's going to keep moving until what?
It doesn't move.
Until it doesn't move. Why would it not move? Why would it change its motion? It's acted on by a force, right? Yeah. There's no reason for it to accelerate if there's no force. There's no force right there in equilibrium because equilibrium is net force of
0.
You got it. All right. So there it goes. Now it's going to go, and then it's going to come back here, and it's going to go bouncy, 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 bouncy. Now you may notice that the last picture and the first picture are pretty much the same thing. So, don't stress out about that. Now, here is your task. I would like you to identify whether each of the quantities listed is at a minimum, at a maximum, or has a value of 0. I had the none in there, and I don't really like the none, so I'm going to leave that as just minimum, maximum, or 0. So you can cross out the none, because none and 0 really mean pretty much the same thing for most of us. So we'll go ahead and leave it at that. I'm going to let you chew on this a little bit. I want you to work on it. I want you to talk about it. I want you to figure it out, and then we will discuss as a group.
So we can work on it in a small group.
Absolutely. Oh my gosh, I did that again. Kind of interpret here. All right, so let's start with A. Is that okay? Yes. And again, I don't have any idea who wrote what, and if you do, then I would strongly encourage you to remember that we're learning, right? This is not a test. This is a learning environment. So we want to be positive. We want to be productive. We want to be helpful and not make fun of somebody for writing something down when it was a group decision. It was just one person who came up here, right? So I just want to make that really, really clear. All right, let's take a look at A. So A has a displacement. They said it was at a maximum. What do you guys think? Do you agree with that?
Yes.
Cool. All right. What about the velocity? Velocity of 0. Does that make sense to people? I just want to make sure. So this is like right at the very moment when you let it go, or you can kind of think about as it's bouncing back and forth. At that maximum displacement, the velocity is going to be 0. That's true. Yeah. Acceleration, they said, was at a minimum. Nick's got his thumb up in the air. Do you guys agree with that? Can you tell me why that should be that should be a minimum? So that means like the biggest negative, right?
Yeah.
And why is that right?
Because it's at the point where the force is greatest. So there's
So big force, whoop, right? Big negative force means a big negative acceleration. That's awesome. Good. Now, I threw energy in here too, right? Which is kind of mean. Sorry about that. Yeah, you know. Maximum potential energy. You guys agree? Cool. And then no kinetic energy. Why is there no kinetic energy?
no velocity.
No velocity, right? So I'm going to write this on here just kind of for my help. And I want to remind you that this is going to be something nice, not only for this week and next week in this unit, but to look at in May. So you may want to write some more things on here just so you have it, so that you can use it down the road. So I'm just going to write a couple more things here to remind myself, like the fact that kinetic energy is 1/2 mv squared, and that it's the velocity that's the thing that we're really looking at, right? The spring potential energy is 1/2. Do you remember what the equation was for that? Kx squared. And so there we're really looking for the x to see if that x is big. And that's going to give us a value here. Now, hold on, I have a question. Displacement, oh no, okay, that's okay, never mind, I'm good. Sorry, I was just kind of processing. The force, how do you find the force?
Depending on the displacement.
It is, it's dependent on the displacement. Remember, that's negative kx, right? So the game is that you've got a negative sign. So if this is really big, then this thing's going to be really little. I'm going to remind myself then, kind of working backwards, that acceleration is equal to force divided by mass, right? This puts a lot of stuff together. This puts a lot of stuff together in here. So force divided by mass is acceleration. So if the force is really small, then that means that the acceleration is going to be really small as well. Okay? Just kind of trying to articulate the thought process that I hope that you had, okay, as we're going through. Velocity is 0 because it's not going anywhere. And the displacement we can measure just directly off of the thing. All right, we're going to go through the other ones a little bit more quickly. Let's just take a look here. So displacement of 0. Velocity is at a maximum. I hear some dissent. How do we feel about this? Why are you saying no?
It's going in the negative direction. Well,
So it's going really, really fast. You with me there? It's going fast, and I think that that's what we were thinking, right? It's going really, really fast, but silly. It's going really fast in the negative direction. So I'm going to change that too. I think that should really be a what? Minimum. Yep. Right idea, just forgetting the direction, and that direction matters. Why is the acceleration 0? Or is it? Because the force is 0, right? The force is 0 because x is 0. Boom, boom. Yeah? Okay. Tell me about the potential energy.
sorry.
Also 0. That's okay. You can turn it off, right?
No, it's the top. It's like a
Okay, whatever.
it rang.
Kinetic energy, it says, is at a minimum. How do we feel about that? Elizabeth, why do you have a thumbs down?
Because for kinetic energy, it's velocity squared.
It's velocity squared. So what does that mean about kinetic energy? It can never be what?
Less than 0.
It can never be less than 0. It can never be negative. So that means that this thing has actually got to be at a maximum, even though this is at a minimum. That's another one of those things to pay attention to and to see. Yeah, these are big things. Can you see why I love this chart? You get it? It's awesome, right? All right. Let's take a look at C. So at C, we have a displacement that is at a minimum. Do you guys agree with that? It's the furthest negative that it can be. I think that's okay. Yeah, just like it was at the furthest positive in A, it's at the furthest negative in C. Have a velocity of 0? How do you know it's got to have a velocity of 0? How do you know it's not moving? Reason that through with me. There's a little bit more that we can do. What's that? It's at a max displacement, so what?
If it's like bouncing, it's not moving for just a second.
It has to, yeah. Jasmine, were you going to say
Yeah, I
something?
was gonna say that.
Yep. The other little thing that I just want to kind of keep in your head, again, because a lot of times they're going to throw funny things at you, and I want to make sure that you kind of put this all in your brain just before it gets to see which way is it moving.
That way.
Negative, right? And just after it gets to see which way is it moving. That way.
This way.
Just before it's at C, it's negative. Just after it's at C, it's a positive. And if you have a negative and you're getting to a positive and it's a continuous function, what do you have to go through?
0.
You have to go through 0. You have to have a velocity of 0. And the velocity of 0 has to happen at that maximum displacement. Okay? Just another kind of way to think about it. Gentlemen, can you stop fighting over pencils, please? It's distracting to me.
Sorry.
Thank you. All right. We've got a minimum displacement. Minimum here, a negative minimum gives you a maximum. So a maximum force gives you a maximum acceleration, so I'm cool with that. Potential energy is at a maximum. Can potential energy, because this is negative. This is a negative number. So why isn't this at a minimum as well? If my displacement is at a minimum, why isn't my potential energy at a minimum? Why, Jonathan? You're super close. It is energy, and generally we don't, well, some kinds of energy can be negative. Remember, if I take my giant orange, and I have my giant orange here, and I call H equals 0 here, and then I ask for the potential energy here, is it negative? It is. So I can have some kinds of potential energy that are negative, but can potential energy of a spring be negative? No, because the 1/2 is a negative, and the K is not negative, and X is what? X is displacement, but displacement is squared. So any negative number is going to turn into a positive when you've got a spring potential energy. So that's important to know that this is going to be at a max instead of a minimum. Just another little catch there to make sure we got. And there's no kinetic energy. Why not? Because it stopped. The velocity is 0. Not going anywhere. All right. D, here we go. D's got a displacement of 0. We good?
Yep.
Velocity of maximum?
Yes.
Acceleration of 0? Because there's what? No force. No force means no acceleration. Hey, no force. Oh, there you go. Potential energy? 0. Maximum kinetic? Cool. All right. Let's look at that last one to make sure we're still on the same page. So how should E and A compare?
There should be the same.
They should be the same. Why, Courtney?
Because they're the same picture.
Because they're the same picture. It's the same story. This one is right before I let it go, right? Boom, and this one is after it's bouncing back and forth and back and forth. So we got maximum, we got 0. This one's going to be actually a minimum. Acceleration is a minimum. Oops. Come on, little thing. And then you've got a minimum force. Let's see, displacement is at a maximum, so this is going to be max as well. Is that okay?
No, I don't really understand that.
Okay, let's do it. Which
Okay.
one? The potential energy one?
Well, yeah, so potential with kinetic. Well, so they have to be, I mean, you can't have a min and a max, because that doesn't make sense. So,
True.
So I got that much.
Cool.
So why is it max for the potential then instead of kinetic?
On this one?
And yeah.
In any one of them?
Any.
Yeah, okay. So we have to look at what it's dependent on. So the potential energy is dependent on X, right? It's dependent on the displacement. So if the displacement is either really big or really small, then the potential energy is going to be big. You with me there? Because X is going to be really big or really, really negative, which is still, the squared will be big.
Oh, so I think I was thinking like maybe that at part C was at equilibrium.
Oh, okay. Okay. Does that help you?
I think it does.
Okay, so then this one here, because it's at a maximum displacement, we're going to have a maximum potential energy. And because this one has a velocity of 0, the kinetic energy is going to be 0 as well. Okay, so you may think you're done with this sheet, but you're really not. Indeed, you're not at all. I would like you to take a minute. If you moved tables and you'd like to go back to your normal seats, you're welcome to. I want you to spend a couple of minutes right now. I want you to look at the sheet as it is now. This is the real physics that I'm asking you to do now. I would like you to find some patterns. I want you to look at this. There are patterns in this data. Okay, there are patterns in this chart. I want you to write down as many patterns as you see. Okay, and then we're going to share them in a minute. Okay, so find some patterns, talk to each other, find what you can find. Okay, so I am going to ask that for this first little bit, I want you to, I want to make sure that this is really accessible to everybody. And by that, I mean, I don't want to throw in like high level math. We will get there. And in fact, on Monday, we're going to actually get there and go there. But for right now, I just want you to tell me about patterns that you see. Okay, does that make sense? So no trig functions is really what I'm trying to say. Okay, not because I don't love them, because I do. I love them a lot. But I also want to make sure that that everybody is comfortable with it. And if they haven't seen it yet, or they're not comfortable with it, that I don't want to scare them. Okay, we'll get there. What's up?
Oh, I just said the first pattern.
You want to tell me a pattern? Do it.
At least in each column we have 0 maximum.
Okay, so each column has, what'd you say?
At least 1 0 maximum.
Hold on.
I mean, I feel like that's like stating, and I don't mean this in a bad way because I think I'm just not understanding what you're saying. I feel like that's stating the obvious. Oh, okay, so it's not really a pattern. It's just more of a,
That is a pattern.
no. Let's try again.
You mean each column has a 0? They all have 0.
I want you to, okay, shh.
Or each row.
One of each. I think that's what he means.
Each row, I mean. Yeah.
No.
Okay. I do understand what you're saying. Let's see if we can find a little bit more subtle patterns than that. Yeah.
Whenever potential energy is at a maximum, it's like every association.
Okay. So whenever potential energy is at a max, kinetic energy is at 0, and vice versa. Okay. That's what I'm looking for. And I don't mean that, I'm not trying to say that you were wrong. This is the kind of thing I'm looking for more. Go, Nick.
In A and B, or sorry, A and C, and in B and D, each column is the same absolute value, like can be the same number, but a couple of them are like opposites. If that makes sense.
I think it does. So you're focusing on A and C for now, right? So you're saying like these ones are not 0 at the same time, and these ones are 0 together. Is that kind of what you mean? Or maybe I'm not understanding.
So in A and C, D is max and C is min. So like the D is like the same. It's just like they're opposite.
Same absolute value?
And so like so each is the same absolute value.
Okay.
Each trait.
Okay, so I like that. So let's see if we can generalize that a little bit more. What is true about A and C in terms of the situation?
They're at the opposite ends.
Yeah. So maybe we can say that when we'll call it a block, is at the maximum displacement, what can we say about everything? Everything's pretty much the absolute values of the values are the same. Is that fair? Yeah. Yeah. Absolute values of the quantities are the same. Cool. Go, Harrison.
Distance and acceleration are opposite each other.
Distance and acceleration or displacement and acceleration are opposite?
Yep.
Awesome. And what do you mean by opposite?
For every max the distance has, acceleration is a min.
Okay. So kind of like we said here with max and zero, but it's max and min every time. So we could say like,
And then when they have zeros, they go to zeros.
okay. Okay. And that is not
Yeah.
trivial by any stretch. So when D is at a max, we can say that A is at a min.
Yeah, and they reach zero at the same time.
Awesome. All right. Bell's going to ring in 3 seconds. So bring this back. I will say, friends, your homework assigned for this weekend, I don't want you to worry about the problems.
All right.
I think I looked over it while you guys were working. I think the questions should be fine. If you want to play with the problems, you can, but I don't think you're quite there yet. I don't think we've covered quite enough. So questions, but don't worry about the problems yet. Have a wonderful weekend. Be safe. It might be a little snowy out, so be careful.
So, Miss Carbley, what do I need to do since I was gone for 2 days?